Here is a full professor, is that right?
I did not know that either.
His research focuses on mathematical reasoning and justification. He's received several awards: Early Career Publication Award in Math Ed from AERA, Early Career Award from the National Science Foundation, Selden Prize for Outstanding Research in Undergrad Math Ed, the Janet Duffin Award for Outstanding Publication in Research and Mathematics Education, and Best Paper Award for the Annual Conference on Research in Undergraduate Math Ed in 2009, 10, and 14. No, come on, smart enough. Anyway, so thank you so much for coming, and thank you, Keith. We look forward to it.
So I should say the reason I'm giving this talk today is Ravit. I gave this talk over the summer and asked for some help from some science ed folks, and I asked Ravit and Clark, but Ravit was busy and said, "Oh, I really want to see your talk. But why don't you go and do it at a brown bag so I could kill two birds with one stone?" I bring that up because Ravit's not here. So if you don't like the talk, you could blame her.
It's Yom Kippur, so I think that's why she's not here.
Drat, ruined my joke. Sorry. So one of the reasons my L&T colleagues sometimes don't like my talk is because they think I'm going to make them do hard math.
Never happened.
Don't worry, I actually will not ask you to do math. I'm bringing this up because this is a common proof in an undergraduate mathematics textbook. And I don't want you to focus too much on the proof, but rather the author. So this proof was written by Euclid, who lived in 300 BC. So this is a proof from 2,300 years ago, yet we still believe the theorem. We still think his explanation is valid, and indeed, we still teach this to students today. We could compare this to Aristotle, who said some profound things and some rather silly things. And if a biologist came in, or if we put this in an undergraduate textbook, and for biology people, we would think that the person was crazy or a nut or something. But we think of Aristotle as a genius, although he was a misogynist as well. So even these mistakes were usually made for interesting reasons, and we would say it's really not responsible to expect somebody to have a scientific result that's still held 2,300 years later. So your reaction when you go back to the Euclid proof is you might say, yeah, all right, lucky guess. But this book came from a book called Euclid's Elements, and that, even in the last century, was still taught in U.S. classrooms as late as the 1950s. So you'd say, why does this matter for an education talk? And the answer is, it matters quite a bit. So contemporary science educators and math educators, and perhaps educators in other disciplines, believe that the epistemology of our disciplines and the practices of the professionals should inform how we teach the courses and how students understand science and math. Both science educators and math educators agree that generating knowledge is a messy process, far messier than we convey in the classroom, and students should be made aware of it. Where they disagree is that most science educators want students to view scientific knowledge as intrinsically tentative and always subject to revision. Many math educators want students to view some mathematical knowledge that is logically deduced, as certain. And both of these conclusions are based on how scientists and mathematicians purportedly practice their craft. So before getting into the guts of the talk, let me just go over a couple of terms I'm going to carry throughout the talk. So I'm going to talk about the status of knowledge, and by certain knowledge, I mean that people would claim that a statement is absolutely certain. I believe it with a personal probability of 1. By reliable knowledge, I'm using a slightly lower bar that you say, I'm willing to entertain the fact that there might be some theoretical doubt in the statement, but there's nothing about that doubt that would warrant any future action on my part. And then I view a knowledge as tentative. By that I mean not reliable, that I have some sufficient doubts that even though I might believe the knowledge in some sense, this still could serve as the warrant for some future actions, some future studies, for instance, funding future studies, for instance. Now, as I said, I'm going to try to avoid making the talk math heavy. I'm not going to talk about the meaning of this claim per se, but I do want to point out that math educators are fond of classifying arguments by the type of evidence that's employed. So most math statements that are interesting deal with a large class of objects or an infinite number of objects. So here I'm saying something about all of the odd integers, and there's infinitely many of them. If you were to look at this claim for all the odd integers, n squared is odd, one of the ways you might try to say, is that claim true, is to look and see if it's true with particular odd integers. We call that an empirical argument. Empirical arguments are thought to be very important, and they increase our confidence that this claim is correct. But in general, mathematicians find these arguments to be unreliable. So they could make good for making tentative claims, but not reliable claims. The reason is whether I check 5 or 10 or 1,000, there's still infinitely many that I haven't checked. So what's the alternative? The alternative is a deductive argument in which I use logic to deduce this fact from the way that these claims were defined. And some believe that deductive arguments can make knowledge reliable or even certain. So the first part of the talk is how do many math education researchers investigate argumentation, and how does this differ from science education? Notice the important caveat here. Mathematics education is a big social science. Any claims that were monolithic are almost bound to be wrong. So I'm describing is probably the majority of my colleagues who investigate these types of issues, but there are people who disagree, so I don't want to lump them all into one category. The main points I want to get at this part of the talk is, as opposed to science educators, mathematics educators do not view mathematical knowledge as tentative. And then when math assertions are justified by deductive arguments, we expect students, if they know what's going on, to have certainty in those assertions that are justified by deductive arguments. So, although there's disagreement among science educators about what the so-called nature of science is, nearly all contemporary science educators believe the nature of science should inform instruction. The idea is that if you don't understand the nature of science, you're not going to be able to understand what scientific claims mean or how they should be evaluated, and this is important for making informed decisions about things like climate change. So one of the particular aspects of the nature of science is that scientific claims are intrinsically tentative. So what I'm showing you here is a recent article by Lee and her colleagues that are looking at the sophistication of the types of arguments that their students produce in science class. And they have a hierarchy of which I show the last 3 levels. What I want you to know about the hierarchy is, yes, we do want scientific claims to be grounded in evidence. We don't just want students to make bald assertions. But at an even higher level, students should recognize that scientific claims are tentative. They should qualify their claims with some doubt and consider possible counter-arguments to their claims. Science education is also a broad field, so I don't want to lump all science educators together, but this is fairly common. Here's another widely used hierarchy that people have used, and notice again, we want our claims to be grounded. It's better to have claims grounded in evidence, but it's better still if we ground our claims and qualify our claims. So we consider reasons to have doubt for those claims. Now in mathematics education, we tend not to have it. In fact, perhaps surprisingly, we go the other way. We say if claims are justified by deductive arguments, you shouldn't have doubt in them, and if you do qualify them, that's a deficiency. So here's a classic and widely cited study in our field. Ephraim Fishbein went to a bunch of high school students and showed them a claim, n cubed minus n was divisible by 6 for all of the integers. Then he showed them a proof of the claim. Then he asked the students, would you like to check this claim with a really large number? What Fishbein found and what he lamented was that there were a lot of students who said, yes, I understand and believe the proof of the claim, but also, yes, I would like to check the claim with a large number. And what Fishbein thought the students lacked was a complementary intuitive acceptance of the absolute predictive capacity of a statement which has formally been proved. Why would you want to check a claim after it's been proved? Now you could say, all right, this is just one study, and it was 35 years ago, but the study continues to be cited today as evidence that students really don't understand what about the nature of mathematics and proof. And there are a lot of other authors who have written that students should gain some type of certainty from deductive evidence, or they should not be seeking further evidence from like their authority or a teacher or other examples of a claim that they've proven or a proof that they've read. So we could go one level deeper and look at the epistemology of science education and math education. A popular epistemology in science education is that of Dina Kuhn. So this is her framework that looks at the sophistication of epistemological stances. And what I want you to notice is that if we look at this, then the idea that there are facts in science is viewed as absolutist and somewhat naive. Now we could of course, Dina Kuhn's epistemology is controversial to some, but I could have used a large number of epistemologies that made a similar point. The idea that there are some facts and that these aren't just the best guess that we have at the time is viewed as naive. In mathematics education, perhaps the most widely used framework to study students' justifications is Harrell and Sauter's proof schemes. Essentially what proof schemes does is it says for the individual, they divide the world of mathematical statements into two types. Conjectures, something I think is true, and facts. And the way a conjecture becomes a fact is if I have a deductive argument. So we have a conjecture, it becomes a fact once the person is certain of the truth. So we have these things that we're certain of. And the way that this happens is via deductive arguments. So it's interesting to compare how would Kuhn evaluate Harrell and Sauter and the many math educators that use their framework. Well, it's not a perfect match, but it would seem that we would fall into the absolutist camp. We're talking about students having facts and wanting them to have facts. So maybe math educators are naive. It's one other point, if I went downstairs to ETPA, and I went to someone, let's say I walked up to Andrew and I go, Andrew, I really think you're taking a deficit perspective in your research. You're a deficitist. He might hit me, right? And if you go to a math education conference and, there are ways you might be able to get hit, say, you're taking a behaviorist stance. That wouldn't go over well. And say, you're an absolutist. They wouldn't like it. So it's very unfashionable. What I'm claiming here isn't that people would avow it, but much of their work is based on it. Let me give you one more example. And I'm glad that Ann Morris isn't in the room or she might hit me. So Ann Morris did a very common type of design that we use in math education research. She took 30 pre-service teachers, gave them some deductive arguments in support of an assertion and some empirical arguments in support of an assertion, and asked them to sort them and see which one would allow you to have certainty. In the theoretical part of the paper, she says deductively derived mathematical conclusions are not absolutely certain. Mathematical knowledge is not infallible. What she's saying is I'm not an absolutist. But this is the abstract of her paper. Only 30% of the population experienced deductively derived conclusions as necessary. 30% experienced deductively derived conclusions as uncertain. So notice the only is saying, gee, we only have 30%, we should have more. The but is saying they made one right inference earlier, but they don't get that deductively derived knowledge is certain. So she also described some of the people who were able to distinguish between the empirical arguments and the deductive and gave representative responses to them. And we have one student saying here, it's more of a mathematical proof, it's probably almost certainly true. Now, if you really didn't have an absolutist perspective, you would want to regard this as pretty good, right? And yet this was regarded as pretty bad. And so the point here isn't to pile on this particular author. This is actually endemic in our field. So the conclusions that I want to draw from this part are many math educator research studies rest on the assumption that if you have a deductive argument that supports a claim, the students, mathematicians recognize that claim is necessarily true, and the students should as well. And this differs from science education, where they want students to have doubt about their claims. So you'd say, well, maybe this isn't that problematic. Mathematical objects and mathematical claims have different epistemological and ontological statuses than scientific claims. Mathematicians and scientists practice the crafts in different ways. Of course, math education researchers and science education researchers should use different frameworks and have different goals. So I want to look at this and say, what's the basis of this? What's the epistemology that we're using when we make these claims? So what I want to say is that the epistemology that we have is based on a caricature of how mathematical proof is practiced with mathematicians. This informs the way that we do our research, but this caricature is also misleading. So any discussion of mathematics epistemology has to be centered around the notion of mathematical proof. Proof has been called the sine qua non, essence, soul, backbone, and guts of mathematics. Virtually any metaphor that can be used to ascribe importance has been used with proof. And the ironic thing is if you ask what is a proof, you either get I don't know or disagreement. Now in science education, there are many science educators who want students to distinguish between hypotheses, theories, and laws. But Douglas Allchin says this effort might be misguided. The boundaries between these three are fuzzy, and they don't really make a difference in scientists' work anyway. This is not the case with proof. So in mathematics, there are a sharp distinction between conjectures and theorems, and a conjecture becomes a theorem exactly when there's a proof of that conjecture. Furthermore, this distinction matters. Once something becomes a theorem, you could use it without further justification in your mathematical work. So in this sense, this actually ties pretty well with what Hurrell and Sauter are doing. So mathematicians, instead of saying conjectures and facts, they really do divide the world into conjectures and theorems. And the distinction does matter. So I'm going to present a caricature of what a proof is. And I should say by a caricature, what I mean is that they're taking something that is true about proof, but they're distorting it. So for instance, and to avoid any political leanings, here are pictures of our last two presidents. Now, these are caricatures, but this isn't what they look like, but they are based on truth. Our last two presidents did have big ears. It's just that we're distorting this to an extent that it's humorous, but it's not quite right. I'm going to argue that we do the same thing with proof. And the way that I think proof is metaphorically viewed is new theorems are logically necessary consequences from a secure base of knowledge. I'll just talk a little bit about a secure base. So I presented this earlier, and I would say this is one of the steps in the proof. Since n is odd, there's an integer k such that n equals 2k plus 1. What would be the justification for that? If you weren't a mathematician, you might say, yeah, sure, I guess that makes sense. Every odd number seems to be an even number plus 1. And yeah, maybe so, but that's not actually the justification a mathematician would use. This is true because this is how we chose to define the odd numbers. So definitions and axioms cannot be right or wrong. They're just declared. They don't have truth values. They're assumed to be true a priori. So the secure base of knowledge in mathematics is sort of imposed by fiat. So I could have a different definition of odd numbers, but if I did, then I would get different true facts about them. And I say something about the odd numbers, implicit in that statement is as the odd numbers are conventionally defined. Now, as an aside, many philosophers question whether there is really a secure base of mathematical knowledge and practice. These discussions are very interesting, but they would take us too far astray. So just for the purposes of the talk, I'll assume that there is. What I'm really interested in the talk is the logical chain that we use to deduce new theorems from the secure base of knowledge. So the idea of a proof is that each step in a proof that is not in the secure base must be a logically necessary consequence of some previous statements in the proof. So what's a logically necessary consequence, and how do we tell? The answer is there's no agreement on this. This is one of the reasons proof is so tough to pin down. But for the purposes of this talk, I'll say that a logically necessary consequence is that there's no conceivable situation where the previous statements could have been true and the new statement could be false. If there is any doubt at all, any conceivable situation, we'd say it wasn't a logically necessary consequence. And then the theorem is the last statement in the proof. So since everything's a logically necessary consequence, so is the theorem. And because the theorem is as secure as the base, we could actually go back and put the theorem into the secure base of knowledge. This leads to a number of beliefs that many mathematicians and math educators hold. So the idea that theorems are definitely true from what I just said. There's interesting sociological beliefs. So an individual person can gain certainty from a proof just by himself or herself. Proofs do not really involve social processes or argumentation just because it's all logical necessity. And so mathematicians do not and need not and do not use sources. And recall what I had said about math educators' practice. This also seems to follow to me from this. Each new assertion is a logically necessary consequence of some of the previous assertions. Therefore, belief in a proven claim should be necessary, not tentative. And further, there's no possible way that a new assertion could hold if the previous assertions are true. We know they're true because they're from the secure base, so we don't need to consider counter-arguments or rebuttals or check other examples, and students should be aware of this as well. So I promised that there wouldn't be any math in the talk. I lied, but this is it, and it only uses high school algebra. Just to give you a sense of how a proof works. Here's a proof where I assume A equals B. I'm going to square both sides. I'm going to multiply both sides by A. I'm going to subtract B squared from both sides, and I hope I don't lose you here. I do a little factoring. Now I'm going to divide A minus B by both sides. But recall that I assumed that A was equal to B. So I could write B plus B equals B, 2B equals B, and then dividing by B, I just proved 2 equals 1. So if you find this a little confusing or amusing, you're not alone. This actually is considered a joke or a riddle amongst mathematicians. And it is because every one of these steps looks right, yet we wind up getting something false. Now what's going on here is that this step, don't worry, I didn't break mathematics. Remember that I assumed that A was equal to B, so when I did this, I was actually dividing by 0. And canceling out a 0 is a no-no. 0 times 3 is 0 times 5, but 3 isn't equal to 5. Nonetheless, this does illustrate two important points. The first is that if proof is a logical chain, the chain is only as strong as its weakest link. I put one bad step in there, and the claim's not only false, it's not even plausible. The second's a little more subtle, that identifying the weakness in these chains is not trivial. As I said, this is a joke to mathematicians because it can trick them, at least on a superficial initial pass through the argument. Now, we knew that something was wrong because we knew 1 was not equal to 2, but what if I got something that looked plausible? What if I got something that was right, but was right for the wrong reason, so to speak? And furthermore, this was 8 steps in high school algebra. The proofs that mathematicians read are 30 pages using 2 alphabets and very abstract concepts. So the idea that an error could creep in, we might say, is non-trivial. So the points I want to make here is math is characterized by proofs, which are deductive arguments that are based on logical necessity that don't admit rebuttals. This informs the absolutist perspectives that math educators have used to investigate these issues. But proofs do not guarantee truth. They might contain an error. So the next part of the talk is the empirical part, and I think it's the part that I think is most interesting. So what I've established so far is that proofs might not provide us with absolute certainty in statements, if only because mathematicians are human beings and human beings make mistakes. But you could say, all right, that's a theoretical concern, but is it a practical concern? Yes, on a superficial initial reading of a silly thing, I might be able to trick them, but what about if we have a diligent review process and we take seriously? Maybe we can't root out every error, but we probably can root out most of the errors to the point that the knowledge is reliable enough. What I'm going to argue is that if we actually look at the practices of mathematicians as they generate mathematics and check mathematics, the first is there is a lot of space for error to creep in. And the second is mathematicians are fully aware of this fact. So their processes are imperfect, and they engage in those imperfect processes willingly. So this is going to be based on 5 papers. I could send you any of these if you like. The first was on a study I did where I looked at 8 mathematicians checking proofs for correctness using verbal protocol analysis. The second was when I asked mathematicians in interviews how and why they read the published proofs of their colleagues. I did that with Pablo. The third was a survey that Pablo and I sent around to 118 mathematicians to check the generality of the qualitative findings from these 2 studies. And the fourth and fifth papers was where we used these studies and a lot of other studies that we conducted with mathematicians, as well as the philosophical literature, to synthesize these results and present accounts about how mathematicians think about math. So I did this study, How Do Mathematicians Check Proofs, on the assumption that this was an authentic part of their practice. Surely if proofs are that important to mathematicians, they must spend a lot of time checking them. What I was surprised is that several of the participants in the study spontaneously remarked to me, this is an odd task because it's something that I don't ordinarily do. So one of the mathematicians says, to be honest, when I read papers, I don't need the proofs. Checking for correctness is not that important to me. Probably, so if he gets to a part that he doesn't understand, he goes, probably, I guess it's true if it was in print or something like that. So the 2 things I want to note here is, 1, he doesn't always check the proofs in the papers. And 2, he's saying that it's probably, I guess it's true. So he's saying it's likely to be true, but it is qualified. There is room for doubt. Same thing I asked when I was asking mathematicians how and why they read proofs. I noticed some of them wouldn't say I read it to be sure the theorem in the paper is true. And I would ask them about it, and I'd sometimes get responses like this. I've certainly encountered mistakes in the published literature, and I'm open to the possibility that there's a mistake. But I'm like, but you act on the assumption it's probably correct? Yeah, that's right, that's right. Again, they don't always check proofs, even though they're open to the possibility that there might be a mistake. So in our survey with 118 mathematicians, Pablo and I asked, is it uncommon for you to believe a proof is correct just because it was published in a journal? The large majority agreed. When you read a proof in a journal, do you sometimes not check the proof for correctness? Again, the majority agreed. And some philosophers have actually taken this one step further and said that many mathematicians, when they do their research, accept results from the published literature as black boxes in their own research, meaning they just use them without checking the rationale for them in the paper. So this might not be bad, provided that we have reliable literature. We have to build on each other's work. Now, I don't know about y'all, but when I submit a paper, I usually get 2 to 5 reviews, the median number being 3. It might surprise you to know that, given the importance of this, that mathematics papers are usually reviewed only by a single referee. So that's pretty odd, especially because they don't just publish anything that's true. The result or the proof has to be interesting, so it seems to assume that all mathematicians agree on what interesting is. But no matter. What this does say is, if there's an error in a paper, we would expect a single mathematician to root it out. So we would expect them to be very diligent, right? Well, it might surprise you to know that mathematicians don't always check every line of a proof that they referee. So this was from the interview about how they read the proofs, and one of the guys goes, I don't always check every step, even when I referee. If the key idea makes sense, probably the rest of the details of the proof are going to work too. Pablo and I were very surprised by this, and when we tried to generalize it, it generalized sort of. So when we asked the mathematicians in our survey, when I referee a manuscript, it's not uncommon that I do not check every line in the proof. 35% agreed. So it wasn't the majority, but it is a substantial number. And just as a caveat, I don't want to say that mathematicians are indifferent to the truth of the theorems or to the correctness of the proofs. So it's uncommon for me to, another question, it's uncommon for me to judge the proof to be correct if I'm sure the main idea or method is correct. And we get almost the same method. So essentially what they're saying is, I'm looking at the chain as a whole rather than the individual links. What about when mathematicians do check every step, an individual step in a proof? What do they do? The answer is a lot of things. It depends on the step, it depends on the mathematician. But what they sometimes do is check the proof, the step in the proof with individual examples. I'm going to go through this quickly because this math is a little bit technical. I'm not sure how many people in the room will follow it. But the key thing here is the guy came to a step in a proof, didn't understand it, and then checked it with a couple examples, 25, 36, 64, and 24 times 24. Do you remember earlier in the talk I presented this slide? That checking things with examples is good for boosting your confidence, but it's generally not reliable? That's exactly what the guy did here. So this actually presents an interesting asymmetry. The way that you would write a proof isn't the way that you would check it. You could use looser standards. One other point, in most of the math education journals that I submit to now, they want me to submit my article blind, to ask who wrote it. The idea is it should be the quality of the ideas rather than the identity of the author that decides whether my results get published. It's debatable whether it is a good practice. I mean, given how much interpretation goes in our field, you might want to know the bias or the meticulousness or the honesty of the researcher before deciding how much trust you have in the results, but we mostly use blind review. Might be interesting for you to know that in mathematics, reviews of math manuscripts are usually single blind, so the author is revealed. And informal conversations with mathematicians say this is very important. Some mathematicians are prone to make mistakes, so I know I got to accept the results carefully. Others are very meticulous, and then I don't need to be as careful. And it goes further. In the thesis of Muller-Hill, she notes that, let's say a famous mathematician comes up with a paper that I have to referee it. He's a famous mathematician, so it'll probably be correct. And so I might say, yes, this really seems plausible, but I'm not really sure it's true. Then you end up with the question, is this because they don't have enough knowledge? So here we go. Mathematicians are getting the benefit of the doubt. Pablo and I also found this out. When I referee a manuscript, it's not uncommon for me to be very confident the proof is correct because it was written by an authoritative source that I trust. We didn't get full generality, but we did get 39% agreement. So, does this matter? The answer, to be honest, is I don't know. There are some mathematicians who say that false proofs are fairly rampant in the literature. Many of us have published proofs that are just plain wrong. And some scholars say that a third to half of the proofs in the literature are wrong. Don't put too much stock in this. Mathematicians are a diverse lot, and if I go around picking quotes, I probably could find mathematicians that would say anything. Nothing's wrong, everything's wrong, half is wrong. What we can say is that at least some mathematicians think there's considerable room for error in the publication process. Now, just stepping back, when I entered this research, I believed the caricature of proof. Proof guarantees truth. So when I got the result that mathematicians would sometimes check proofs by example or trust authorities, I was put in a bit of a bind. So either one of two things was true. The first is that these types of empirical, probabilistic sourcing checks can provide certainty. The other is if they can't, then the purpose of proof was not to provide certainty. And I think the latter view is correct. There's a trade-off before guaranteeing or ensuring correctness in the amount of time that we can expect mathematicians to reasonably take to check things. So they engage in practices that they know that admits error, but they do so because it would be infeasible to generate much mathematics if they adopted any alternative. I think anyone would agree that the likelihood of catching errors in proofs or not making them would be increased if, one, we use multiple referees, two, you would only use a published theorem if you personally checked its proof and didn't just trust the result in the literature, three, insist that the referees check every line of the proof, and then fourth, write subproofs for every proof in addition to example checks. That could only help, but nobody's pushing to do that. Well, I shouldn't say nobody, there's a few fringe mathematicians. Most aren't pushing to do that. So the point here is in math practice, mathematicians sometimes are not writing proofs to obtain certainty. The practices that they engage in, they know do not attain certainty. They wittingly leave room for error. And there's also an asymmetry between how you can write and justify a claim and how you can check the justification. At this stage, you probably think that I'm saying that we shouldn't trust mathematical knowledge. Do I really believe that? Do I really think that maybe there's only a finite number of primes? No, I think that some mathematical knowledge is indeed very reliable. And this brings us to the question of why that's the case. If it's not from the caricature, a single line of secure logical reasoning, then what is it? So what I'm going to say is it's not because we check a single proof or a single line of reasoning, but we use multiple sources to obtain reliability. Those multiple sources include sourcing. It includes building better chains, and I'll explain that in a minute. And it's saying that the metaphor of the chain might actually be the problem, that mathematics isn't a chain, it's a cable. So first, by sourcing, what I mean is that when mathematicians consider the correctness of an argument or a claim, they're considering things that aren't within the claim or the argument itself, but more its cultural surroundings. Where did the claim appear? Who wrote it? Who checked it? So one of the things that Pablo and I asked the mathematicians is, when I read a proof in a respected journal, it's not uncommon for the quality of the journal to increase my confidence that the proof is correct. The majority of the mathematicians agreed with this. And just as an aside, I don't really know why this is true. Like why mathematicians would do that. Is it because better journals have better referees, better authors, better editors? It's a bit of a mystery to me. I'll talk with Brian, probably has some opinions, and maybe he'll explain it to me after the talk.
No, not one.
So one of the things we also found, both in our interviews and with this, is that when I read a proof in a respected journal, it's not uncommon for me to be very confident that the proof is correct because it's written by an authoritative source that I trust. Some mathematicians are known for rarely making mistakes, and then you believe them if they say they prove something. But it's not just the author of the proof. For really hard proofs to check, sometimes mathematicians don't have the ability or time to check it themselves, even for really important theorems in their field. So what Nathanson writes goes, in those cases, there are bosses who proclaim the correctness or incorrectness of a new result. If it's an easy proof, you can check it yourself, but if it's a hard proof, if a complete proof would be 100,000 pages long, then we rely on the judgments of the bosses in the field. Now, so sourcing matters. One last thing. The Clay Mathematics Institute made 7 problems for the millennial, they call the millennial prizes and the millennial problems. If you're able to prove or disprove these statements, they'll give you $1 million. But they have to be sure that you actually did prove or disprove the statements. Before they'll consider the proof, the proposed solution must be published in a journal of worldwide repute, and it must have general acceptance in the mathematical community 2 years after. So, all right, we get it. Has to be published in a good journal. I told you that. 2 years after. Why 2 years? Standards of proof change, but not that quickly. Something that was right 2 years ago should be right today. The reason, I think, is that when we check a proof and say it's correct, what we're really saying is we haven't found an error in it. So it's kind of a probabilistic judgment. The more time you leave for the field to find an error, the more likely an error would be found, should it exist. What I want to highlight here is, you might look at this and go, yeah, of course we use sourcing. Why would mathematics be different than anything else? It's that in our literature, this is very controversial. So there's actually an article that just came out, not just came out, in the Journal of Literacy Research in 2011 that said mathematics is different than history and science because history and science use sourcing and mathematicians don't. We also have our literature saying we shouldn't have students trusting the words of their teachers. They shouldn't even seek their teacher's approval to gain confidence in what they deduced. We certainly don't want things to be decided by democracy. So the idea that we're using sourcing in mathematics, obvious as it may seem, is actually very surprising in some circles. The other thing I want to say is that if proof is based on a logical chain, one of the ways that we gain confidence is by building better chains. It might surprise you to know that after mathematicians prove something, they'll often prove it again. Remember Euclid's proof that I showed you from 300 BC? People are still publishing different proofs of that theorem today. This all seems very odd. The reason that they're doing this isn't because they doubt Euclid's proof per se, but you get new insight from finding different ways of finding out why things are true. But John Dawson provided an interesting analysis of why mathematicians reprove theorems. So if you enjoy mathematics and mathematical thinking, I think this is a pretty cool paper that I'd recommend you read. And one of his reasons is new proofs employ reasoning that is simpler or more perspicacious, more understandable than previous proofs. So I'm returning to this proof here, and as I said, I won't make you check it, but I do want you to notice one thing. This proof uses variables and algebraic equations. Algebra was invented in the 16th century. Euclid wrote this proof in 300 BC. This isn't Euclid's proof. What we did was recast Euclid's proof using modern notation, representation, and methods of reasoning. These methods of reasoning are much easier to verify and thought to be much more secure. The confidence that we have in this argument is based in part by the translation. We have a better chain than what Euclid originally produced. This happens a lot in mathematics. So Stephen Krantz came up with an example that there was a fellow by the name of Louis de Brange, I might have pronounced the name wrong, and there's a famous conjecture, I don't understand it, called the Bierverbrach conjecture, and his first proof was 326 pages. He worked with a team of Russians and got it down to 16 pages and published it. Somebody read his proof and saw that they could take some shortcuts and knock it down to 8 pages. And then a graduate student at Stanford actually published it in his dissertation as 4 pages. De Brange's proof used areas such as de Brange functions, the Lohner equation, the Esti-Garsper inequality. Now you're probably thinking, I don't know what the hell any of these things mean. Neither do I. I don't know what these things mean either. Einstein saw a 4-page proof used only ideas from undergraduate mathematics. You can see why we would gain much more confidence from this proof than we would from this proof. The final thing to think about is the chain the right evidence, the right metaphor at all? And so what John Dawson wrote is an overarching purpose that is overlooked with reproving theorems is one that is analogous to the role of confirmation in the natural sciences. Different proofs are in effect replications. So Dawson cited Peirce and said the mathematical reasoning forms a chain, not a chain, which is only as strong as its weakest link, but a cable. Most mathematical results are so involved in the general web of theorems that they can be reached in so many ways that their incorrectness is simply unthinkable. There are 400 proofs, at least, of the Pythagorean theorem. Even if half of them are wrong, we know we have 200 that are right, and we only need one. Just as a general point, is that this doesn't just apply to proofs. So Roger Boas, who edited a journal called the Mathematical Review, tried to summarize every paper published in a mathematics academic journal in the world, said of all the new results reviewed, most are true, but the corresponding proofs are perhaps half the time plain wrong. So this illustrates an important point, that even when we make a mistake in a proof, the result is usually true. And one reason is we often have a lot of confidence in the result before we even try to write the proofs. We often use empirical evidence, analogy, and all that to think about that. So when we have confidence and reliability in the results, it's not just because we have the proof. It's because we have the proof and a lot of other inductive supporting evidence. So, in summary, mathematical knowledge is reliable to individual mathematicians, but it's not because they have a single logical chain that deduces it. Non-deductive evidence, particularly sourcing, plays an important role. And multiple arguments, or viewing the mathematics as a cable, not a chain, also does this. So the final part of this, I'll wrap up. I know not many of you are math educators, but I'll give a few education thoughts about this, is that one thing that we do know is, what I'm not claiming is that math classrooms should exactly mirror mathematical practice. That's impossible, that's infeasible. Same thing is true for science classrooms. You can't actually have scientists, students do everything scientists do. They don't have the equipment and background theories and so on. What we can say is that, at least historically, instruction based on bad epistemologies or inaccurate epistemologies have tended to be bad instruction. People think the scientific method in science has done a lot of harm. The exclusive focus on symbols that dominated math philosophy in the 50s led to the new math movement, which is now widely considered to be a disaster, and it actually set math education back about 30 years because no one trusted us for a generation. So we should think carefully about whether our instructional goals are appropriate given mathematical practice. Now, in general, math education researchers have been critical for students when they do the following things. If they see a proven statement but still express some doubt or want some checks and want to check in it, we view them as deficient. If they want to check whether a proven statement works for particular examples, we view them as deficient. If they write a proof but are unsure about it and then go to their teacher or friend to check, we view them as deficient. We should think really hard about whether that we should do that. If we want to view them as deficient because mathematicians don't do those things, then we don't have the grounds. If nothing else, I tried to convince you that mathematicians do each of these things. I also think that this is good practice. Why shouldn't students trust mathematicians and help them figuring out holes in the reasoning? Why shouldn't students seek multiple arguments in support of the same claim? Why shouldn't they try to improve their arguments so they're more understandable? The other point is more of a meta point with how we do research here. And I'm just going to make a broad point that's in the math education and maybe the learning sciences literature more generally. We could evaluate students' behavior through two lenses. One might be called the expert's lens or the observer lens. So I look at that, and I have some view about what students should do, maybe informed by my own understanding or mathematician's practice. And then I sort students by whether they're doing, I sort them into the categories that I define and then judge them whether they're in the right categories. And that research has its place. Ultimately, if we want to go and say 70% of the students have such and such a skill, we have to be able to document what such and such a skill is and what would be the right answer and so on. The other is what Joanne Lobato called an actor-oriented perspective, where the idea is instead of trying to judge a student as right or wrong, I want to try to understand what the student is doing from the student's point of view. Now, most of the research that I showed you in the beginning of the talk was of the first type. I give the students some task or ask them to evaluate some argument. I look at what they do and I say they were supposed to do that or they were not supposed to do that. It's only recently that researchers, this is kind of surprising because math educators have tended to take the actor-oriented perspective in other areas, but it's only recently that researchers have looked at, with regard to justification, what is it that students are trying to do? Instead of saying, are their justifications good or bad, what is the reason for their justifications? And in all the studies of this type, at least the ones that I cited here, it turns out when students are doing something ostensibly wrong, they often have a very good reason for it. And so one of the cases that we could take is trying to understand the students' motivations for accepting these arguments paints them as far more nuanced and rational than the initial interpretations and inferences that we make. Thank you for that. And yeah, if you want my teachers, I have a website here where they can be downloaded.
Great, thank you so much. We'll take questions.
So many.
Yes.
Really interesting things, and we'll talk more, I'm sure. But as a mathematician, I might push a little bit on the way you're using the word proof. And if you replace it with the word argument, then then it makes a little bit more sense. And so separating the two of those, argument being sort of the artifact created by a human, and then proof being